Hello, welcome to this new video from Guidance Education channel. We are continuing class 11 chemistry, chapter 2, atomic structure. We will see the topics that are discussed. We are continuing developments that led to Bohr model of atom. Under that, we have already discussed the dual nature of electromagnetic radiation. In this video, we will discuss atomic spectra of hydrogen. But before that, we will introduce ourselves to spectroscopy, the technique used by scientists to study atomic spectra. We will see atomic spectra types, emission spectrum, continuous and line spectrum, and then pass on to line spectrum of hydrogen and its explanations. This is a very important topic, so do not skip the video. Watch the video completely so that you get all points clear. And if you think the video is useful, like the video, share the video, and also give me your feedbacks in the form of comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now. Thank you. We will pass on to the topic. In this video, we will discuss atomic spectra. What is the significance of atomic spectra? Study of atomic spectra has provided evidence for quantized electronic energy, which is proof for particle nature of electromagnetic radiation. We have already seen that electromagnetic spectrum consists of an array of electromagnetic radiations with a range of frequencies or wavelengths. Among these radiations, it is only the white light portion which is visible to us. It is called visible spectrum and consists of 7 colors. Spectroscopy is the study of spectra. It is a branch of science. Instruments used in spectroscopy are of two types: the spectroscope and the spectrograph. The spectroscope consists of a prism which causes diffraction and dispersion of the light, and a telescope which helps to examine the rays that emerge from the prism. What is a spectrograph? In a spectrograph, also there is a prism. Instead of the telescope, it uses a photographic plate. An image of the emergent radiation is obtained on the photographic plate. On the basis of whether the radiations are emitted or absorbed, the spectra are classified into two: emission spectrum and absorption spectrum. In an emission spectrum, all the radiations emerging from the source is obtained on the photographic plate. In the case of absorption spectrum, radiation from a source is made to pass through the sample of a substance and then subject to spectrography. The photographic plate will show only those colors which are not absorbed. There will be certain dark lines on the photographic plate corresponding to those wavelengths which are absorbed by the substance. In this video, we will be discussing only emission spectrum. Emission spectrum is further classified into two: continuous spectrum and line spectrum. Let us first understand continuous spectra. I have provided two diagrams here. We will consider the first diagram. You have already learned dispersion of white light when it is passed through a prism. Image of the emergent rays are seen on the photographic plate. All the 7 colors are seen on the photographic plate as continuous spectrum. That is, the various colors are not distinctly separated. One color merges with the next, then with the next, and so on. Violet with the least wavelength bends more than red, which has the maximum wavelength. Hope you have understood continuous spectrum. Now we will understand line spectra. This topic is more important because our topic is atomic spectra, and atomic spectra are line spectra. A small amount of sodium chloride is taken in a platinum spatula and it is heated over a flame. The atoms in the molecule of sodium chloride absorb energy and get excited. The energy released by the excited sodium chloride is passed through the prism. The photographic plate shows only the presence of two yellow lines with a gap. It is discontinuous and such a discontinuous spectrum is called line spectrum. You have to note one important point. What is analyzed is not the light from the flame, but the radiation emitted from the excited material or sample of material. Now we will pass on to line spectrum of hydrogen, that is atomic spectrum for hydrogen gas. A sample of hydrogen is electrically excited. It absorbs energy, then starts emitting energy from it. That energy is passed through the spectrograph. The radiation gets split into several lines on the photographic plate. They are seen as five distinct groups, each group containing several lines. Each line in every group corresponds to a particular wavelength of the electromagnetic spectrum. The lines as well as the groups are distinct and having discrete frequencies. The spectrum obtained is discontinuous and it is a line spectrum. You can see in the picture the groups as well as the lines are separated by clear spacing. The various frequencies in the line spectrum of hydrogen was further studied by scientists. These groups were named after the scientists: Lyman series, Balmer series, Bastian series, Brackett series, and P-Fund series. It was found that the wavelength of Lyman series correspond to ultraviolet rays of the electromagnetic spectrum. Similarly, Balmer series correspond to visible part. Bastian series, Brackett series, and P-Fund series correspond to infrared of the electromagnetic spectrum. Even a small amount of a sample of a substance will contain very large number of atoms. When subject to electric field, the atoms get excited by absorbing energy. When the energy increases, they become unstable. Then they release energy in order to become stable. Now we will proceed to understand the studies done by Balmer and Johannes Rydberg in explaining these series. Line spectrum of hydrogen atom was explained to some extent by Balmer and Johannes Rydberg. But first we will take up explanation given by Balmer. But before that, I will just explain the diagram that I have given. N1, N2, N3, N4, N infinity and so on. All these are energy levels around the atom where electrons are present. The energy of an electron present in the energy level will be equal to the energy of that level. The energy level of these various levels ranging from 1 to infinity goes on increasing. When electrons get excited by absorbing energy, they get transported from the lower energy level to the higher energy level. And when they lose energy, they move back from higher energy level to lower energy level. In the diagram, three series are represented. Balmer explained the Balmer series corresponding to visible part of the spectrum. That is this portion. Johannes Rydberg extended the findings of Balmer to the other series as well. We will see the details. Okay. Balmer in 1885 conducted several experiments, and on the basis of the experiment, he put forward a formula to calculate the wave number of the spectral lines in the Balmer series. He suggested that the spectral lines can be expressed in terms of wave number. You are already familiar with the term wave number. It is a property of a wave and it is the number of waves present in unit length of the wave. And this is the symbol. According to him, the wave number is equal to 109,677 into 1 by 2 raised to 2 minus 1 by n raised to 2 per centimeter, where n is an integer equal to 3, 4, 5, etc. From this diagram, we can understand that it is the wave number of the energy released when electrons from the higher energy levels lose energy and move down to the second energy level. So in Balmer's equation, this N refers to energy levels higher than second energy level, that is third, fourth, fifth, etc. Okay, remember this is only for Balmer series. Balmer series is the spectral lines visible when electrons lose energy and get transported to the second energy level. Later on, Johannes Rydberg modified the formula and made it applicable to all spectral lines in the different series. According to Rydberg, the wave number is equal to 109,677 into 1 by n1 square minus 1 by n2 square per centimeter. Number of waves per centimeter. That is the meaning. Okay. What does n1 represent? N1 may be equal to 1, 2, 3 and so on. It corresponds to the energy level to which the electron losing energy is getting transported. For example, for Lyman series, N1 is equal to 1. For Balmer series, it is equal to 2 and so on. And N2 is equal to N1 plus 1, N1 plus 2, N1 plus 3 and so on. It corresponds to the higher energy level from which the electron is getting transported. I hope you understand. Let us try to apply this concept in the case of Lyman series. There are 5 spectral lines. The length of these lines are different as they are getting transported from different energy levels. N2 for these spectral lines will be N1 plus 1, N1 plus 2, N1 plus 3, N1 plus 4 and N1 plus 5. N1 plus 5 will be for those electrons which are getting transported from the sixth energy level. This formula can be applied to calculate the wave number of any spectral lines belonging to any series. Okay, this number is called Rydberg constant. Hydrogen atom is the simplest atom and the line spectrum for hydrogen is the simplest. As the molecule becomes larger, it becomes more and more complex. It was further observed that there are some common features for all line spectra. For example, number 1, line spectra for each element is unique. Point number 2, the line spectra showed regularity. Now, scientists wanted to know what the reason was for this similarity. Later on, these questions were answered and this helped in understanding the electronic structure of elements. So, we have discussed atomic spectra or line spectra of hydrogen atom. Hope this video was of great use to you. If it was useful, consider subscribing my channel. In the next video, we will discuss absorption spectrum before we pass on to Bohr atomic model. Bye for the present. Thank you.